Welcome to qnawire.
In problem 132, we're asked to find the centroid of this bowl as well as its contents, and we'll just find the bowl for part A. Now the centroid in the x and z direction are going to be equal to 0 because of symmetry, but we do need to find the centroid in the y direction. And to do that, we'll use the centroid in the y direction times the total area of the bowl is equal to the sum of the centroid in the y direction of each component times its area. And the two components are going to be the wall of the bowl as well as the base of the bowl. Now the wall is the trickier part, so let's start there. We need to find the individual centroid and area of the wall. And to do that, we'll use this equation. Now the same equation actually, but written in a different way. So the centroid of the wall times the area of the wall is equal to the integral of the centroid of the element dA. And the element we're integrating is going to be a small section of the wall which will be ds, that length, that tiny length that we're integrating, and it'll be equal to the arc length formula, which is radius times the derivative of theta. But to find the area of the wall, which is equal to the integral of that derivative area, we need to multiply that derivative side length times the circumference, and the circumference of a circle is 2 pi r, except we have to multiply it by sine theta to get that the point on the wall, because the circumference increases as you go up the wall. And by multiplying by sine theta, we get the actual circumference at whatever point on the wall, depending on theta. And so multiplying that by ds, we'll get the differential area, actually, not the total area. So let me rewrite that. And so plugging in ds, that's r d theta. Now we can integrate to find the area of the wall. We're going to integrate from pi over 6 to pi over 2. This pi over 2 is going to be 90 degrees, but the pi over 6 is to where it meets the base, because doing a little trigonometry, you can find that this is equal to 30 degrees. So then we plug in dA. In solving the integral, we get the area of the wall to be pi square root of 3 times the radius squared. Now we also need to find the centroid of the wall itself. So going back to our equation, for the centroid of the wall. Means that equal to the integral of the centroid of the differential element. And the differential element of the wall is going to be equal to negative r, because it's in the negative y direction, times cosine theta, which will give us the y value on any point in the wall as we take the integral over the entire section of the wall. So plugging that in, we have the integral from pi over 6 to pi over 2 of that differential element times dA, which we found earlier. And then we get that the centroid of the wall times the area of the wall is equal to negative 3/4 pi r cubed. So now we just need to find the area and centroid of the base. The area of the base is just going to be a circle. So really a fourth of a circle, so pi r squared over 4. Because, well, actually, it's really just a circle, but it's because the radius in this case is actually the diameter, which is a little bit confusing. But they gave us the radius as of the base is equal to the r value they gave us, and then the centroid of the base is going to be equal to this side length here. And so we just multiply the cosine of 60 degrees times the radius, which is also negative square root of 3 over 2 times r, to get that distance. And now we know everything that we need to plug into the equation of the centroid of the entire bowl. So you plug in the area of the wall plus the area of the base, instead equal to the sum of the centroid times area of the wall plus the area of the wall times its centroid, of the base times its centroid. We get that the centroid of the bowl is equal to negative 121.9 millimeters from the top of the bowl. Now moving on to part B, we are looking for the centroid of the bowl filled with punch. And again, we have that symmetry gives us a centroid of 0 for the z and x directions. And looking at the punch, it'll make the same shape as the bowl, just a little smaller. Although they say that the thickness of the bowl is negligible since it's so small. So actually the radius will be the same, radius of r to the edge of the punch. And so the height will be the same as well. That's square root of 3 over 2r. The differential element for the punch is going to be a slice through it. Like so. A cylindrical slice. That's a distance y from the top of the bowl, and a thickness dy for that differential element, with a distance x to the edge of the bowl, or rather the edge of the punch. And to find the centroid in the y direction, we'll use this equation again, where the centroid times the volume is equal to the integral of the centroid in the y directions of that differential element. First, let's find the volume, which is equal to the integral dv, or the differential volume of that slice through the punch is equal to pi times r squared minus y squared dy, since the area of the line of a circle is x squared plus y squared is equal to r squared. So then we can plug in dv to our volume. To find the volume. We're going to integrate from the bottom of the bowl, negative square root of 3 over 2r, to the top, which is 0. Solving the integral, we get that the volume of the punch is 3/8 pi times the square root of 3 times r cubed. And now we need to find the right side of our centroid equation, the integral of the centroid of that differential element. That integral will also be from the bottom to the top of the punch volume. And our differential element is going to be y. because we're integrating along the y-axis, and the differential slice is going to be at any point y, variable y, from the top to the bottom of the punch. And then we found dv earlier, and we can just plug in dv. And then solving this equation on this integral, we get that's equal to negative 15 over 64 pi r to the fourth. Now we know everything we need to find the centroid using this equation. So we plug in the volume we found of 3/8 pi square root of 3r cubed, instead of equal to this the integral of the centroid of the differential element on the right side of this equation. We get that the centroid of the punch itself is located